Computer. Okay, so go ahead and talk about this. If you haven't turned in the activity, please turn it in to Canvas under the Assignments tab. You just have to upload a file to that, and I can grade that after that. And so we have class today and on Thursday, and I'll record those and post those to YouTube. We're going to start with chapter 2, which is IR spectroscopy today. Most of today is going to be a lot of the theory and kind of things to look for. And we might get into some of the functional groups as well today. We'll see how far we go. And then what we'll do is I will be assigning tonight the homework questions for mass spec. And so those will be, actually that's up for debate. If we would want to use the activity as our homework grade instead of actual homework, who would consider that to be a useful part of your time, to use the activity as your homework grade instead of a separate homework assignment? You can vote in the chat room there if you want. Or do you feel that you would like that, extra little bit of homework graded so that you can get feedback for it? It would be about 10 questions, and it would be, what's the molecular ion peak in the mass unit? What's the exact mass? And look at these different ones and identify which of these mass spectrum would be associated with which. So it'd be like similar to the activity, but you'd be doing it on your own. So either more practice is good, right? So one of the reasons I'm kind of thinking about doing this is because as we move forward, we're gonna have mass spec, and we saw its limitations. We couldn't actually tell exactly what it was because we were missing some information. Okay, and so by adding IR, we're gonna do that too. But as we go forward, each exam is gonna have a mass spec, an IR, an NMR, and then we're gonna keep adding the different things. Okay, well, the homework's not really worth that much, so I can assign a set of homework grades and you can turn it in. And so it's only about 5 or 10% of the grade anyway, so go ahead, and I think you're right, practice is better, but I just wanted to get a feel on that. So, so I'll assign those today, and they'll be doing about a week. And then again, they'll be uploaded to Canvas in some shape or form. Okay, now we got that under our belts. Let's go ahead. I'm going to share my screen, and I'm going to start with the slides for IR. And come on, iPad. Yay. All right. So, so this has some additional information from what's in the book about the theory. I like to have a little bit about the theory in here because if, trying to get my gallery view over here. If you have an idea of where the things come from, it'll start to make sense on why different things are in different places. And so, well, there's going to be, a couple of homework questions on what the theory is. The practical aspect of this is being able to use the IR to give you identification. And so that's how we're going to use it for exams. However, we will, on the activity, I might ask a couple questions about the theory that we can work through. So, but let's start with that. And as many of you know, the electromagnetic spectrum is, light we see and light we don't see. And it goes everywhere from radio frequencies with, mile-long wavelengths all the way down to gamma rays, which are very small. Nuclear, can actually look at the nucleus of an atom because the magnetic radiation has such a small wavelength. And so if you can imagine, from that radio frequency, actually it'll give you some idea about the magnetic field within a nucleus. Microwave radiation actually tells us something about rotation of atoms. We can actually do rotational analysis of individual atoms in vacuum using microwave. And then we have IR. And IR tells us a lot about the vibrations and the change in the dipole moment of materials. And then we have the stuff we see right here in the middle. And then once we go to that, we go to the ultraviolet, and in ultraviolet, that's where we're starting to excite electrons from a ground state to an excited state, a previously unoccupied molecular orbital. So we're going from our HOMO to our LUMO, and so we're actually moving electrons from there. In IR, we're absorbing energy and changing the vibration. In UV, we're actually exciting electrons out into other orbitals. And then, of course, when we get into X-rays and stuff, now we start into ionizing radiation where you can break stuff apart. Okay, so what we're going to be dealing with is just this nice little area just below the visible where we can actually absorb energy and cause a change in dipole moment. And that change in dipole moment, we can say, it gives us a little bit of information about structure, but what we're going to see is it gives us a lot of information about functional groups. Okay, so when we're talking about absorption bands within the IR, we have a couple different things to think about. The first thing we think about is position, and position is where it lies on the x-axis, okay? And the whole reason the positions change has to do with two things. One, the mass of the two atoms that are bound together, okay? And we call that the reduced mass because it's the combination of the two masses. And so if you think about it, something with a very light atom here and a very heavy atom here will be able to vibrate much faster than two heavy atoms because you have to move mass, okay? So that position on there has everything to do with the mass of those two atoms. The other thing, though, it has is how strong the bond is. If you have a single bond between two atoms, you can have a little more of deflection in that bond length than if you had a double bond, because now you have a pi bond and a sigma bond competing. And when you go to a triple bond, you now have two pi bonds and a sigma bond. And therefore, as that bond order increases, as the number of bonds increases, the frequency also increases, okay? Because you're binding them tighter and tighter, and therefore it can't vibrate as much, okay? So that tells us where it's gonna be on the y-axis, okay? I'm sorry, x-axis. The strength or the absorption ability or how big the peak is on the y-axis has everything to do with the change in polarity. Okay, so if you have a very non-polar system, you might not see a very big change. But if you have a very polar group, like a carbonyl group in particular, you have a big change in polarity when it absorbs, and therefore you can see an intense band when you see it. The last thing we look at is how wide or narrow the bands are. Okay, the narrower the band is, that means it has only one mode which it can vibrate on, and it only absorbs in this very narrow energy range. However, if some bands can be hydrogen bonding, and that hydrogen bonding is very dynamic. And so you can be hydrogen bond to 1, 2, or 3 atoms, okay? All 3 of those give rise to different absorptions. That's why things that hydrogen bond tend to be very broad in their peak, where things that don't hydrogen bond or have a very small window of absorption have very narrow bands. So our position is about mass and bond stiffness. The amount it absorbs is all about the change in polarity, and the width is all about hydrogen bond. Okay, so let's look at that and kind of get our heads on that. So in this particular example here, oops, I've got to do this, sorry. Save files. Where'd you go? Oh, there we go. Sorry, I was in a screen where it wouldn't let me annotate. So there we go. So in this one right here, what we want to do is we want to look at just this carbon-hydrogen bond. Okay, so carbon at molecular weight of 12, hydrogen molecular atomic weight of 1. And so there's a big difference between those, and that hydrogen is a very light atom, and it has a single bond between the two. So it's going to vibrate at a fairly high frequency. In that case, it happens to be right around 3,000 wave numbers, okay? Just by changing the mass of hydrogen from 1 to 2, going from hydrogen to deuterium, we've actually decreased that frequency significantly. We can tell when something's been deuterated because that frequency changes. Now, going from a molecular weight of 2 for deuterium and going all the way up to a molecular weight of 16 or an atomic weight of 16, we see another drop in frequency. That change in frequency has everything to do with having two heavier atoms. And again, going up to chlorine, which has an atomic weight of 35, it drops again, okay? So that's just the idea that the mass of the atoms is related to that frequency. And there's actually a way to calculate that. We're not going to, but I wanted to show you that there is one. It's that the frequency, or the average frequency that we think it's going to vibrate at, is 1 pi over the with the speed of light here. But this right here is the bond force. Okay, so that's the bond force in dyne. So how strong the bond is, and this is the a unit of that takes into account the masses of the individual atoms. So it's the mass of atom A times mass of atom B divided by the sum of those. And that gives us a unit. So our mass is on the denominator, our force constant's on the numerator. And so that shows that both will change our frequency significantly. And the mass change, if we went and calculated it, we would be able to calculate these frequencies fairly well. Okay. Now, let's go to bond order. Okay. So in the next area here, instead of changing atoms, I'm going to just use carbon and oxygen. So mass is no longer an issue. So any change in frequency has everything to do with that bond strength, or the force of the bond, right? So that bond strength. And so if we go with carbon monoxide here, which has a carbon-oxygen triple bond, we see a fairly high frequency, okay? And that's because the bond length between those is very short, and it's bound by a total of 3 different bonds, the sigma bond and those 2 pi bonds, okay? Now, by breaking one of those pi bonds and allowing that bond to lengthen slightly, we see a drop in frequency. And then by breaking the pi bond completely and only having the sigma bond between the carbon and oxygen, we see another decrease. Okay, so frequency has everything to do with the mass of the atoms and the bond order of the atoms. And they're combined in this equation here, and this is called Hooke's law. And so that we can see that they are interwoven. We cannot separate one without the other. Okay. So the other thing we need to think about when we think about IR spectroscopy is that you have to absorb photons. Okay. Okay. And so the whole idea of the spectrum is that some of the photons are of the correct energy that can be absorbed. And when they are absorbed, they are not strong enough to excite electrons, but they are enough to excite the molecule to vibrate more. Okay, so really we're absorbing light that causes a change in heat, basically, and it gives it more vibration. Okay. So whenever we have these things happen, there's going to be a bunch of different types of vibrations available to us. The simplest vibration we have is between 2 atoms, and it would be a stretch. And so we can have just the 2 atoms move apart and move back together. And that's the simplest way we can do it. But if we have more than 2 atoms, we actually have a wide range of things that can happen. We have bending motions, and we have wagging motions, and we have other things. Now, because we're not moving along a single axis, our dielectric constant doesn't change as much. And when our dielectric constant doesn't change as much, it means it tends to be a weaker interaction. And just because something wiggles doesn't mean it's necessarily important to identify the functional group. The stretching vibrations tend to be more indicative of our functional groups. Okay, so let me kind of explain that a little bit more. Okay, so in the case of carbon dioxide, okay, you're thinking, oh, it's a nice symmetrical molecule, and so if we have a symmetric stretch, okay, we can change the dipole. First of all, let's look at what the dipole is just to start with. Okay, so based on the idea that carbon is less electronegative than oxygen, we're going to have oxygen pulling electron density to that side. And on the other side, we have the other oxygen pulling it there. And so we have a net 0 dipole because without vibration, we have an equal amount of electron density being pulled toward the oxygens, and they are in a line, and that's equal and opposite. So in theory, it's a non-polar molecule, but each of the bonds is polar. Okay. So if we're starting with something that itself is non-polar, how do we get a good IR absorption in the system like we see for CO2? And the reason we do that, because we can also have different stretch modes now that we're exciting it with photons. So if we excited it with photons such that it gives the vibration that is symmetrical, so every time it stretches out, it stretches back. So both oxygens are stretching out at the same time and stretching back at the same time, okay? That's the symmetric stretch, okay? But that symmetric stretch does not change the dipole. So that means our symmetric stretch in CO2 is not a major contributor to absorption because it doesn't change the dipole. Okay. So let's take that in contrast and say, okay, let's say this oxygen is moving in this direction, this oxygen's moving in that direction, and this carbon's also moving in this direction, okay? That means that one of those carbon-oxygen double bonds is getting longer. One of those carbon-oxygen bonds is staying the same or getting shorter. So now we have an asymmetric stretch. When we have an asymmetric stretch, we have a net change in dipole. And our net change in dipole actually goes in that direction, and therefore we do see this absorb in the IR, okay? The frequency, the energy of light that allowed it to make that symmetric stretch allows for that asymmetric stretch, okay? Now, you know, it's a linear molecule, but it still can actually bend slightly. So if we had those functions here, when we bend this up here, and we take both of these oxygens and push them down like this, okay? There's a slight change in dipole, but remember the oxygens are the major contributors to the dipole. So unless you're wagging this, you know, 10 or 15 degrees out of plane, you're not going to see a big change. And therefore this bending mode is not necessarily highly active, but it does have a slight change in polarity. Therefore we can see it. But I bet the energy is going to be a little different than this major contributor of the asymmetric stretch. Okay, questions on that? We're still looking at that change in dipole and those bond strengths.
So this, I have a question.
Yes.
So this asymmetric stretch changes the polarity of the molecule?
Yes,
okay.
because one of the bonds is getting longer and one of the bonds is getting shorter. That means they can't pull equally in both directions.
And one more thing, like changing in polarity means changing in dipole.
Yes.
Okay.
Change in dipole is what we're going to be seeing. All right. So let's look at that a little bit differently now. Let's think of the old concept that our bond is not fixed, okay? It's not a steel rod between two nuclei, right? Because we have those electron clouds, we have some flexibility in those nuclei being attracted to each other and repulsing each other, okay? And that springiness comes from the fact that we have those electron shells on the outside, and those aren't fixed either. So we have an opportunity to have a little bit of springiness. Now, the numbers we state for bond length in other chemistry courses, that's the equilibrium bond length. That was the bond length that was measured when we don't add any external forces. Okay. So in the case of IR, we're actually adding an external force. We're adding a little more heat such that we're making that spring more in and out of that equilibrium bond length. And so when they are moved away from each other, we're actually, now they have a little more attractive force to each other and they'll spring back, okay? When you're pushing them together, they actually have a little more nuclei, positive charge force against. So our spring force is all about trying to maintain that equilibrium bond length. Okay, and that spring force is, the net charge of the nuclei and the net charge of the electrons around it, trying to keep it at that nice equilibrium distance. Okay, so now if we have this vibration here, we need to disrupt that vibration with absorbing a proton. Okay, so what this means is that when we start our molecule out at a lowest ground state energy, it's going to have that average bond length that it's going to maintain. And then once you add energy to the system, those bond lengths are going to fluctuate more. Your average bond length will remain the same. However, the individual bond lengths are actually longer and shorter than they were before you added energy to the system. So that means the more vibrational energy you're adding to the system by absorbing a photon, the larger the change in the average bond length. So the max bond length is bigger with the more energy you change, and the max bond contraction is bigger than in the standard ground state. So by adding energy to the system, you're seeing this greater change in bond length over that period of time. It still has that energy. So how can we use that? Okay. Well, the other thing to think about is that we're not just adding energy to the system. We also have more than one mode available to us. And so for a compound that only has two atoms, we only have that one force, that asymmetric and symmetric spring right here. But once we start to hit nonlinear molecules here, we still have those asymmetric spring stretching and those symmetric spring stretching, but then we also have actual mass of the atoms moving in a bunch of different directions, okay? So, so as we start seeing more and more complex molecules, we might see more and more things that are absorbing energy, but not necessarily all of those bands that are absorbing energy are going to be helpful to us in identifying compounds. But some of them are going to be very helpful to us. For example, the symmetrical stretch can be very helpful to us if it's changing the dipole. The asymmetric stretch typically changes the dipole, so we can see that much better. Some of the bending and wagging are going to be much lower in energy and be much less intense because they don't change the dipole nearly as much as the symmetric or asymmetric stretches. Okay, so that brings us down to what the machine looks like, and I hope you've all seen one and got to play with one. But the idea here is that we actually are shooting light through our sample, and if it's absorbed, it causes molecular vibration. And if it's absorbed, that means it doesn't get back to the detector, and therefore we see an absorption in our spectrum. Okay. If it does completely pass through all our material and get back to the detector, that means that frequency of light was not something that could be absorbed by the sample, and therefore it just shoots right through. Okay, so that's why most infrared spectra are traditionally displayed as percent transmission, because everything that went through, we really don't care about. We only want to see what didn't go through, because that's telling us what's being absorbed. And what's being absorbed should correlate to a functional group or a type of bond and a type of mass. Okay. So let's take our bending and wagging and our asymmetric and symmetric stretches here and look at them just as a function of the infrared spectrum of exhaling breath into the IR, okay? So a lot of the times, if you've ever prepped IR, you actually close it and let it purge for a couple of minutes to make sure that all the CO2 from your breath is eliminated. However, in this one, I want to show you the difference between the bending motions and the asymmetric and the symmetric stretches and where they show up in the spectrum. Okay, so in the case of this, I'm going to look at this water first, okay? And in water here, the peaks up here are in this high frequency range, which means we're looking at the vibration of just the heavy atom, light atom. We're looking at that vibration, that change in bond polarity, okay? So there's a change in that, but the dipole is not changing very much. So we have a high frequency, but we don't really have a very strong signal, okay? Once we get into here, this is where we start to see the wagging in the symmetrical and unsymmetrical wagging and the interface between the all three atoms together, okay? And that's a lower energy. So we start seeing absorptions in a lower energy. And again, those have very little absorption, very little change in dipole. So they don't absorb very much. So notice I don't have a symmetrical CO2 here, because the symmetrical CO2 stretch is actually non-active because we don't change the dipole. However, the unsymmetrical CO2 stretch, where we have one bond getting shorter and one bond getting longer, this one's getting shorter, this one's getting longer, we see that there's a dramatic change in there, and it's associated with this energy, but notice how big the peak is here? Because the dipole is changing significantly with this unsymmetric stretch, we see a strong absorption in that field. That means most of the photons that are of that energy got absorbed to allow that molecule to do this unsymmetric stretch. And notice this is the one where we had the bending mode, where it was it's kind of changing the dipole a little bit, but they kind of cancel out a little bit. So it's much lower energy and not as strong. Okay, so I'm hoping that you're seeing that, okay, mass plays a big role in where the frequencies are, and the change in dipole tells us a lot about the strength of the spectrum. Okay, questions on that? Okay. Now, because it's associated with an energy along the x-axis and a number of photons that can be absorbed along the y-axis, we can actually quantize or actually calculate out the energy there. And we know that the change in energy is equal to Planck's constant times the stretching frequency, okay? And so what we'll see is that when we think about this and we actually measure this, value here, we're going to see that it is less than 5 kcals per mole. And that is important because the idea is that that's not very big. And so that most of our changes in energy are very small, smaller than 5 kcals per mole. And that means that they're associated with that energy of light, which means that this energy is less than that of the energy found in visible red light. And that's why we have the infrared or the below red photons are the ones that do our absorption. Okay, so it's all about that change in energy between the stretching frequency that gives us our possibility to see this in this low energy frequency of light or magnetic spectrum. Okay, all right, so that's the bulk of the theory. So the idea is, how can we use this to our advantage? Okay, so the three things I want to draw attention to in this one here is that this is our typical infrared spectrum, okay? And it's just basically a plot of energy versus how many photons got absorbed, okay? So when we look at this one right here, we have frequencies from 4,000 wave numbers to 400 wave numbers. That's the typical span for there. And actually, we can recalculate this from wave numbers to actually electron volts. And if we did that, we'd see that we would have less than 2 electron volts going down to about 0.1 electron volts in energy. So we're looking at a very low energy portion of the spectrum, okay? The other thing we're looking at here is that this is percent transmission. So if 100% of the light went through your sample, that means nothing was absorbed. So in these areas here, very few photons are being absorbed or scattered by your sample, okay? So it's rarely 100% because there's usually some scattering and some, you know, extraneous absorptions here and there. But the key here is that when you start seeing these stronger peaks at specific frequencies, we can start to say, yes, there's a significant change in the dipole in that specific area, and it should be associated with a particular atom-atom combo, in the fact that, you know, like the mass change or a double bond, a triple bond, a single bond, those will change in direction here, but the strength here is our change in dipole. Okay, questions on that? Okay. Okay, so IR gives us a lot of information, and it all is about the molecular structure. And occasionally it's the intermolecular structure for the case of hydrogen bonding. But basically, the structure controls the number of photons absorbed because of that change in dipole, that ability to absorb that photon and vibrate. Okay, so structure controls that. And so structure also controls the stretching frequency, because structure is carbon and hydrogen is one frequency, carbon and carbon is a different frequency, and carbon and oxygen is a different frequency. So structure controls both the x-axis and the y-axis. So we can get a lot of information from like the compare and contrast of the two. Okay. So the way to think about that is that the intensity of the IR peak is controlled by the change in dipole moment. Okay, so from the ground state and the excited state, there's going to be a change in dipole moment. And therefore, the greater that change, or the greater the number of possible dipoles that can change, the greater the absorption in the peak. Okay, so a way to think about this is if you look at any one bond and you think about the polarity between those two atoms, the bigger the polarity difference between those two atoms, or the bigger an electronegativity difference between them, the more likely you are to have a strong photon absorption. Okay, so that kind of leads into this, where the delta En, which is change, the difference in electronegativity between the two atoms, increases the dipole. Okay, now a longer bond length also increases the dipole. The greater the dipole, the greater the absorption. Okay, so, but again, not all symmetrical and unsymmetrical bonds or vibrations contribute to your IR. So things that are very nonpolar, like a carbon-carbon bond, they can be very, very weak, or maybe even absent or hidden under other peaks, because there's almost no change in dipole, because there's almost no change in electronegativity. Okay, so that leads us to the idea that even though we have 100 bonds in our molecule, not all of them are going to be IR active. Okay, so the polar bonds are usually IR active, and the non-polar bonds in symmetrical molecules can be very, very weak, or maybe not see them at all. And it's all in the fact that you're still not changing a dipole enough to get enough photons absorbing to make that vibrational change. Okay, so an example of that would be in acetone here. This is a carbon right here, and this is an oxygen here, which means we have a strong dipole in this direction. We have a fixed dipole before we ever start irradiating the molecule. And now it has a certain energy associated with that. And so when it does absorb those photons, it absorbs them very strongly and has a strong dipole. So typically for most carbonyl compounds, carbon-oxygen double bonds here, we have a very strong peak. Okay. Now, we're going to keep the same bond order, which is a double bond here, but we're going to change out one of the oxygens with carbon here. Now, this particular molecule is completely symmetrical. And so that when we actually vibrate along that carbon-carbon double bond, we don't even see it, because there's no change in dipole. And so we don't see it very well at all. However, by just changing the mass from one side of the molecule and the other side of the molecule, we now have a mass difference between those two sides of that double bond. And we will see it because there is a slightly higher change in that dipole moment because we have different masses on the thing. So we're getting an unsymmetrical vibration because we have a light side and a heavy side. The light side is going to vibrate a little faster. So we're going to see a slight difference. And so what we'll see is that we get a peak, but it's going to be weak because, again, still the electronegativity of carbon is the same as the electronegativity of carbon. Okay. Now, sometimes I've seen some papers where they go, oh, this is obviously this carbon-carbon bond that's exactly here in this part of the molecule. And it's a very small, very weak peak. And it's like, well, maybe. We have to be careful that not all weak peaks are always discernible. They could be overtones of other things. Okay? So what we want to do is be careful of excluding symmetrical functional groups because the absence of a peak. So for example, this carbon-carbon double bond here would be hard to see on the system, but we would be able to identify it by our mass spec and our hydrogen deficiency index. Okay. Okay. So this is a restating of Hooke's law to remind you that the bond order or the number of bonds between things increases that frequency, okay? And so as we go from a single bond, we're gonna have a lower energy necessary to create that vibration. When we go to the double bond, that vibration is going to be higher because of that. And we're gonna have a higher frequency or a higher, or a more higher energy, higher frequency because it's bound so much more together. So by combining the concept of the masses are part of this and the bond forces are part of this, that means we can calculate, well, we've already had it calculated, all the different functional groups and where they should show up on our IR spectrum. Okay, just like with mass spec, there are strengths and weaknesses to IR. Mass spec has the limitation of we really can't tell connectivity. We can occasionally tell fragmentation, but we can't say absolutely whether we have certain things or not, okay? IR alone cannot determine the entire structure. It cannot determine the entire connectivity of a compound because we cannot see all the different peaks there. Some signals may be ambiguous. You might see a lot of peaks, especially in what we call the fingerprint region, that might be overtones or just, you know, adding 3 different bonds together. And it may look significant, but they might be ambiguous. IR is best at telling us which functional group is there, okay? And it's great when you're doing synthesis or something where you want to tell the functional group change in something. It's usually good to tell us a functional group and functional group change. If we don't have any signal in that area at all, it's a pretty good idea that we don't have that functional group. However, that you can trick yourself with some functional groups, so where you want to look for additional information. We can actually use a sample's IR spectrum to confirm the identity of a compound if you are comparing it to a known sample in a library. Now, this comes down to that last zone, the low energy zone, which we call the fingerprint region. The more the fingerprint region overlaps between your known sample and your unknown sample, the more likely it is to be a good match for that exact chemical compound. Because that fingerprint region, well, it's hard to determine exactly which frequency it is. They are reproducible and definitely matchable, especially with computers. All right, the question is on the strength and or limitations of IR.
On the third bullet point, when you talked about the functional group being indicated and it's good for synthesis, looking at the change in the functional group's presence or absence, are you referring to taking a spectrum of like your reactant and then after the synthesis looking at the product?
Correct. Like, let's say we're going to oxidize an alcohol to a carbonyl. Alcohol shows up in one region because it has that oxygen hydrogen, and that's a high frequency bond. And then we're switching it to a carbonyl, which is a carbon oxygen, which is in a different area because that's a similar masses, but a double bond. So we can actually watch a group switch from one part of the spectrum to a different part of the spectrum and know that we've changed it. Does that make sense?
Yes, thank you.
Okay, so what I like to do is I like to break this down. In organic, I teach only 4 zones, but in this class, I have an extra zone here, and we call it the 5 zones to do it. Technically, we shouldn't really rely on identifying any compounds in this area we call the fingerprint region. However, it is very valuable to research because you can compare it to known compounds in the research library, and you'll get a lot of, it's a 99% match with this, but we will not be using the fingerprint region to identify structure in our materials. We're going to use the 5 other zones predominantly to identify functional groups, okay? So they're kind of laid out from the highest to the lowest here. And so the first one I want to talk about is what we would expect is that highest frequency band should be a heavy atom and a light atom, okay? And that should be the highest frequency of things because we have something heavy holding it down and the light atom being able to vibrate. Okay. So when we look at that, the first thing comes to mind is alcohols. And it typically gives us a very broad band in this 3200 to 3700 range. Okay. It's strong because there's a big change in dipole. It is also broad because of hydrogen bonding. It's very difficult unless you have a dilute solution of an alcohol in some other solvent. You will always see hydrogen bonding in your system. Okay. So the next thing we'll see in this region is this 34 to 3250 to 3340, and that's the alkyne hydrogen. Okay. Now, because the carbon is so tightly bound to the other carbon here, that frequency is a little bit higher. And the other thing I want to draw attention to is this is an sp1 or an sp hybridized carbon in this area here. And you're going to see a trend. Just keep it. So basically, it is, it only has it has 2 pi bonds, which means we have an sp hybridized carbon. The next thing we have is we have oxygen, which is more electronegative than nitrogen. But nitrogen is still a heavy atom compared to hydrogen, and therefore the frequency of that then shows up. And we have it in this 35 to 3300 range. Okay. Now, because the electronegativity difference between nitrogen and hydrogen is not as high as in oxygen, we still have a slightly weaker signal. It's still usually there, and it's occasionally broad, especially if it's hydrogen bonded. But the hydrogen in the amine compounds do not hydrogen bond as strongly as in the alcohol compounds. Okay. So that's zone 1. Everything up there is some kind of hydrogen with a heavy atom. Okay. So let's move down to zone 2, which is 3200 to 2500. Okay. So this is kind of one of those bridge points where we're looking for aromatic versus non-aromatic hydrocarbon bonds. Right? So the first thing we want to look at is the highest N here, and these typically are right above 3000. And those are the aryl or vinyl hydrogens. Now notice these are sp2 hydrogens. This was an sp hydrogen, these are sp2 hydrogens, okay? Because that bond order of the bond to carbon, it changes the frequency slightly. Okay? And this varies quite a bit. The more symmetrical it is, the weaker it's going to be. The less symmetrical it is, the stronger it's going to be. So we can actually see, that is, it varies quite a bit. And that more symmetrical versus less symmetrical is a general guideline. It's not necessarily a hard and fast rule. The next one down here is now an sp3 hybridize, a tetrahedral carbon, okay? And those are always below 3,000 into that, 2850 range. And again, it's also variable, kind of based on what's bonded near it and how symmetrical that bond is. Okay. The next one down is the aldehyde hydrogen, okay? Remember, in an aldehyde, you have a carbonyl with a hydrogen hanging off it. And it's the idea that, this carbon is actually more polarized bond than the carbon-carbon double bond, which is why it's shifted slightly. And it has technically 2 peaks. It says 2 peaks here. The 2900, it's usually covered up by something else. But this is one of the few things that absorbs at this 2700. So when you see a 2700 peak, start thinking, might be an aldehyde, let's do it. These typically are fairly sharp and medium in intensity. But again, this first peak here is usually covered up by other things. For example, anything that was here is going to cover it up. So you got to be careful with that. The next thing is the carboxylic acid OH. Okay. Why is the carboxylic acid OH not up with the alcohols? Because of conjugation with the carbonyl, and because the idea it can be deprotonated more easily, it's more acidic, it actually weakens that bond and makes it vibrate at a slightly lower frequency. But it's still hydrogen bonds, which is why it's always very broad, and it's usually pretty strong. And what we'll see is that it'll be a big hump with all these little other aryl and vinyl and alkyl hydrogens kind of poking out of it. It has a distinct look to it, and you'll be able to check that out. And I added this one right here. There is a unique peak in this area here where it is right at 2600. It's usually weak, but it's the only thing in that zone. And it's the thiol hydrogen. And again, we're going from hydrogen bond strength. This is the biggest difference in electronegativity. Next biggest, and thiol actually has the electronegativity difference between the sulfur and the hydrogen is so low it does not technically hydrogen bond. So we're looking at those different actual molecular factors controlling our vibration and our vibration strength. Okay, any questions about zone 1 or zone 2? Okay. So, and just knowing these general regions to look for things is where it'll get you on your first guess at what different compounds are when you just start looking at a spectrum. And then diving in a little deeper to get a little more information. Okay, the next zone is what we call zone 3. It's between 2000 and 2300. And again, there's only 2 things that show up here. And it's the carbon-carbon triple bond and the carbon-nitrogen triple bond. In theory, we would see carbon monoxide here, but it's an individual molecule. So there's only one of them. So we don't actually list it in this table. Okay, and they both show up about this range. They're typically very sharp. However, it's not always very strong. We might see it to be, I'll show you some examples where it's typically very sharp, but the intensity might be high or low depending on how many we have in a compound. So that takes us into zone 4, the carbonyl zone, okay? Now, for a carbonyl, it's the carbon double bonded to oxygen here. You'd think that it'd all be in a much narrower band, but whatever's attached to that carbon changes that electron density around that carbon. We need to think of that changing electron density around that carbon as changing its ability to where it's going to be on that spectrum. So the first thing we have here is we have the ketone, which is having 2 carbons hooked to our carbon here. And that's going to give us a representative frequency in the 1750 to 1705. And they're always very strong. Excuse me. Let me get a sip of water. Okay, by just adding an electronegative atom from an ester to that carbon, we've shifted it up, okay? So we've gone from the 17th, we've taken that lower band here and shifted it up. Okay, so it's the 1750 to 1735. And again, always very strong. Okay. In the case of the aldehyde, we have one carbon and one hydrogen. Hydrogen cannot donate electron density, and so we see a change again, the 1740 to the 1720. So if you see this plus a peak at 2700, you're starting to identify functional groups right away just by looking at two peaks. The carboxylic acid, because you have that OH, it actually shifts it a little bit lower, right here, to the 1725 to 1700. And the amide, because that nitrogen is less electronegative than oxygen, gives us our lowest frequency in the 1690 to 1650 range. So we can actually watch functional group transformations going from carboxylic acids, aldehydes, ketones. We can see them change as that peak shifts, and we should be able to discern the difference. And we'll show you examples of each. Okay, now that brings us to what I consider our last major zone, which is zone 5, okay? This is where we start to see our carbon-carbon double bonds, specifically in our bonds for benzene, okay? Now, this is the last general one that gives us much information, because once we get below that 1500 range, we start to get carbon-carbon single bonds, carbon-oxygen single bonds. This really gets very muddy, and a whole bunch of different different things can overlap in that region. So really, this is one of the last functional groups we're going to look for, is this carbon-carbon double bond and the aromatic carbon-carbon double bonds. Okay, so what again I want you to look at is look for the functional groups in each zone. Just get familiar with what the functional groups are again and where you expect to find them. Do not memorize the frequencies. You're going to get to use the book. So, but I want you to have a good idea of saying, ooh, let me look here first. Okay, just because you should be able to recognize, you know, a few of the functional groups. So now what I want to do is, let's see, we have time. Yes. All right. I want to go actually look at representative IR spectrum of different functional groups and show you how things change from place to place to place. Okay. So the first thing I want to look at is an alkyne. Okay. So alkyne was in our group 1. It's one of those frequencies where we have a carbon hydrogen bond. And so we expect to see it to be in that above 3200 range, and it's typically fairly sharp. Okay. So what we see here is the first one right here is this carbon hydrogen stretch at the end right here. And that's very indicative of that alkynyl hydrogen. The next thing we see is this hydrocarbon. Notice these are all below 3000. Here's our 3000 mark. So these are the CHs on an sp3 hybridized carbon. All right, here. And notice that, you know, they're actually fairly strong. We have a lot of these right here, so we can actually see them pretty well. And then the next thing we see in our spectrum here is our carbon-carbon triple bond. Notice this is right around 2200, and there's a very sharp, clean peak in that range. Okay. Now, this is where our 1500 mark is, and we don't get as much information out of that region, but for example, this is probably a carbon-carbon single bond for sp3 carbons. However, it could be overlapped with other things. But we can clearly identify our alkyne from these two peaks here, and the fact that it's got other hydrocarbons on it with the remaining major functional peaks. Questions? Okay. So what we'll see is as our functional groups change, we're going to have pretty consistent peak shapes. And so you want to look at the shape of the peak, the strength of the peak, and the location of the peak.
I have a question.
Yes.
These peaks are just because of stretching?
Well, technically, it's because that functional group can absorb that energy of photons and cause it to vibrate molecularly, yes. all of these are stretching vibrations, yes. But think of it as that specific energy of light was absorbed by that functional group to generate that stretch, okay? And because that was a good, and because there's a big change in dipole, it can absorb a lot of those photons, okay? Okay, so let's look at alkenes now. So we're going to go from an sp hybridized carbon to an sp2 hybridized carbon. And what we see here is that this is our 3000 mark. When we look at the 3000 mark, we want to look at things below it tend to be the sp3 hybridized carbon hydrogens, but things above it tend to be the sp2 hybridized or sp hybridized. And notice there's a nice clean sharp peak right above 3000 right here. And we also have a nice crisp peak here at 1650. That's telling us we have a carbon-carbon bond, double bond here. This big peak here is all of the rest of the aliphatic hydrocarbons, the sp3 carbons. So we have, this is our hydrogen on our alkene. This is our alkene carbon-carbon double bond. And then this is the remaining of the hydrogen. Notice there's some peaks down here, and I bet that one's a carbon-carbon single peak, but again, we'll use the computer to say how close we are to that exact compound. All right, so let's move on to the alcohol group, okay? In this case, we have a straight chain alcohol, meaning we have no double or triple bonds. So we don't see any peaks above this 3000 mark here, only below it. So that tells us we have an aliphatic alcohol. And we have this big, broad peak right here above 3000, okay? And it's centered right around 3200, okay? That is the classical OH peak, okay? It's big, it's broad, and above 3000, okay? Now, if we dig deep into the table, we can see that this peak way down here at about 1050 is our carbon-oxygen peak. But again, that carbon-oxygen peak itself doesn't identify this functional group. If you had this functional group and you tried to make an ether out of it and this peak went away, this peak would be our new functional group indicator. But just wanted to, this is not important for the identification of our alcohol. Okay, moving into our next zone, our carbonyl zone, let's look at our ketone. Our ketone here, in this case, is centered at 1718 right here. Notice how strong, narrow, and sharp it is. This is very indicative of most carbonyls will be this very strong peak, almost all the way down to zero transmission. Again, our 3000 mark is here, oops, kind of there, telling us we only have aliphatic hydrogens, which indicates the other half of here. And none of these are identifiable in our 5 zones. Okay. So if we modify that ketone and turn it into an aldehyde, here's what we're going to see. Okay. Again, the first peak at 2900 is probably obscured underneath this because of these aliphatic carbon-hydrogen stretches here. So we can't really identify it as a true 1900 peak. However, this nice little sharp peak here at 2700 is telling us we have an aldehyde hydrogen. And to support that, we have this carbonyl right here, and that's between 1700 and 1750 range. So the combination of this plus this peak is telling us aldehyde. Okay. One or the other doesn't tell us. Both of them do. Okay, so let's move on to a carbonyl that's actually conjugated. Okay, so now we're going to see something a little interesting in the fact that we have our our sp2 hybridized carbons are right here, barely shifted right here. We have our carbonyl peak, but we also have right next to it, this is our C double bond O peak. This is our C double bond C peak, okay? And see how they are really close together? Now, because the carbonyl is in conjugation with that, this right here, it actually moves the carbonyl pack down closer to that carbon-carbon double bond. You'll see that happen a bunch. If they're conjugated, that carbonyl moves closer to the carbon-carbon double bond. If they're not conjugated, you'll see those two more clearly separated. We'll have a couple of examples next week on that. Next class. All right. So now we've changed from our carbonyl to having an electronegative oxygen attached to it. When we do that, it shifts the peak up. We go from that 1725-ish area almost to 1750 because this oxygen is more electronegative than there, and it shifts it up slightly. Notice it's still very clean, very strong, and so that's, again, all our carbonyls should look like this. And we also have no peaks above 3000, so we have a nice long aliphatic chain. Okay, so when we take this and hydrolyze it to get to our carboxylic acid, now we see a slightly different feature. Remember, an alcohol itself is going to give us a nice, big, broad peak up here, centered around 3200. Okay, that's the OH for an alcohol. Okay, but because that carboxylic acid has that acidic proton, we actually have that broad peak is now overlaying the peaks at 3000. Okay, so what we see is this broadening peak right here that's the base peak, and then all of our carbon hydrogen peaks show up underneath it. And so that's what these peaks are the blue ones here. But this OH here is this broad peak under here. Okay. And of course, we also have our carbonyl. Our carbonyl right here is right around 1720. Notice it's shift down slightly, but it is because of the idea that it's hydrogen bonding back and forth. There. I'm sorry, not hydrogen bonding, it's conjugated. Okay, so let's go into that last zone, our zone 5. Our zone 5 was the alkenes area, which is the carbon-carbon double bond. And what we see here is, first, in this particular sample, we have a methyl group. So we do have sp3 carbons, but we have a majority of them being these sp2s. And so these hydrogens on the benzene ring are the ones just above 3000, which are the ones we see here. The hydrogens on this methyl group are the ones below 3000 here. And our carbon-carbon double bonds here, here, here are showing up at these two spaces here. Notice where this is right around 1500, but this is that 1550 to 1565. Okay, so for the last two things I want to do is I want to take everything we just learned and apply it to solving a problem, okay? So what I've done already is I said, okay, from mass spec, we've been able to generate this idea that we have a C6H12O2, and I've already calculated out the hydrogen deficiency of 1. So that means I have one ring or one pi bond here. Okay. Now, use either the chat room or unmute and talk to me. What's the first thing you think you see here?
The broad peak.
The broad peak here, okay, and that is?
carboxylic.
I see in the chat we have an OH right
Yes.
here. Is it a carboxylic acid?
Yes. Maybe.
Is it a carboxylic acid? No,
No.
it's not a carboxylic acid because the carboxylic acid would be here, but it'd be a bit
Okay.
there.
Oh, yes, yes.
So, okay, so we have an OH, great. So we have an alcohol, okay? And looking at our thing here, well, that accounts for one of our oxygens. So let's see what else we have. Okay, our hydrogen deficiency index is 1. And if you look at it right here, if we draw a line right here, we don't see any hydrogen
C.
above our 3,000 mark. So that means we don't have an alkene and we don't have a benzene ring, okay? So that means all of these down here are gonna be aliphatic CH2s, and that's good. We don't have enough hydrogen deficiency to have a benzene ring anyway, so good. That supports our IR is now supporting our hydrogen deficiency index. Ooh, what's next? Oh, what's this here? A C double bond O. I agree with you completely there. A C double bond O. The carbonyl, and it's right at just about 1700. So if it's a, let's see. So we have an OH here on this side. We have a carbonyl here on this side. We don't have a carboxylic acid. So that means that carbonyl is isolated from the alcohol. Okay, so can we draw out the actual structure? Ooh, aldehyde. Is it an aldehyde? Let's see. Is there a peak at 2700? There'd be a peak right here if there's an aldehyde.
Ketone and alcohol.
Okay. So we definitely have an alcohol, we definitely have a carbonyl, and we do not have a carboxylic acid. Okay. Can we write out the answer for the actual structure? No, we cannot. This is just telling us our functional groups, right? We got information from our mass spec to tell us what atoms were there and what some of the general connections were. We have functional groups told us 2 from our 5 zones of our IR, okay? We are not done yet. We would need additional information to absolutely solve the problem, okay? So did I, okay. Okay, okay, so let's go step by step. So again, we found the OH peak. There was no nitrogen and there was not enough hydrogen deficiency, so we're not worried about an aldehyde being under here. Let's see what else we saw. We saw no vinyl aerial because we don't see any peaks there. We didn't see the 2700 peak, so we don't have an aldehyde. And we didn't see the broad peak underneath here, so we didn't have the carboxylic acid. So that was right. Looking in that third zone, we have no carbon triple bonds or nitrogen triple bonds. And we didn't have the hydrogen deficiency index anyway, so we weren't even looking for those. Look to the last one right here. 1700, probably a ketone. Can't be an ester because we didn't have enough oxygens because we already had an alcohol over here. Can't be an aldehyde because we didn't have the 2700 peak. Can't be a carboxylic acid here. Can't be an amide because of nitrogen. Okay, so we are down to a ketone and an alcohol. And there's nothing, no benzene rings and no alkenes in that last band. So we did really well. We have a carbonyl that's and an alcohol on our system. We couldn't tell this exact structure. We might have seen something in the mass spec by losing this fragment here and losing that fragment there, but we still cannot identify that actual structure without probably NMR. NMR would told us a lot about this structure, and we'll get to that in the next chapter. Okay, let's do one more before we break for the day. Okay. And gosh, this C8H7N looks really familiar, but let's identify it by IR and look what we're looking for, okay? So when we do our hydrogen deficiency index, we see that we have hydrogen deficiency of 6, okay? Which, number one, almost always says, probably have a benzene ring and something else in there, okay? So let's go ahead and vinyl hydrogen. In this spectrum, we see a vinyl hydrogen. I think I definitely see an sp2 hydrogen here somewhere. Okay, so let's start identifying our bands one by one. So first of all, everything above 3,000, we have a nitrogen, but we don't have a big peak here. So I don't think we have an amine, okay? This is the nitrogen peaks would tend to be bigger than that. So these are probably just some kind of anomalous peaks because they're not really strong enough to be an amide. So we don't have an amide or an amine right here. Come on, there we go. And we don't have an alcohol because we don't have an oxygen and we don't have a peak here. So we don't have those. And it looks like we don't have a nitrile, I'm sorry, an alkynyl hydrogen, okay? Because there's nothing strong enough. So let's look at our next zone here. If we look at it, we have peaks above and below the 3,000 mark. So that's supporting the idea we have a benzene ring, okay? We have the right hydrogen deficiency to have a benzene ring, and we seem to have some hydrogens above that 3,000 mark, okay? But we also have some below that 3,000 mark. So we gotta be thinking that, there might be an aliphatic portion as well. And we have enough hydrogens and enough carbons to do that. So we have to keep both of these in mind, okay? We don't have that 1,700 peak, and we also don't have a carbonyl, so we don't have an aldehyde, and we don't have a carboxylic acid. So we're just ticking off functional groups as we go. Okay. The next thing we're going to look at is that zone 3. Zone 3, we have a peak. We have a nice, strong, thin peak, and that means that we either have an alkyne or a nitrile. Can't really tell which at this point, but we have an alkyne or a nitrile, okay? If we had an alkyne, do we have a terminal alkyne? Meaning we have a hydrogen on it? No, because we don't have anything in this range here, so we can't have an alkyne with a hydrogen on it. We can have an alkyne somewhere shoved in the middle, but we'll keep that on as a possibility, okay? But we have if we had the nitrile, that would use up one of those nitrogens for sure. Let's look at zone 5. Zone 5 is we're looking for carbonyls, okay? First of all, there's no oxygen in the mass spec analysis, so it's good that we don't see anything in this carbonyl zone. And let's look at the last zone, the carbon-carbon double bond zone. And we do see 2 strong peaks in that carbon-carbon double bond zone, one at 1,600 and one at 1,500. And that's pretty indicative of a benzene ring because it has peaks in both areas there. So we think we have a benzene ring, we think we have a nitrile, and we think we have at least some aliphatic hydrogens, okay? And we might be able to get this one to work together, but the actual structure is we have these two hydrogens here, which are the peak here. We have the benzene hydrogens, which are the peaks there. We have the nitriles, which are these. And then we have the carbon-carbon double bonds, which are these 2 peaks here, okay? So we were able to eliminate a whole bunch of functional groups, get us down to nitrile, benzene, and maybe a CH2, CH2, CH2 somewhere, just by our analysis. All right, questions? Okay. All right, so this is how I want you to use the 5 zones and IR spectroscopy. I want you to start eliminating the possibility of certain functional groups. And when we're given an example where we have the mass spec gives us something about the elements available, the IR tells us how they're hooked together as far as functional groups go. Does it give us absolute identification? Most of the time, no. Okay, so let's see. 3 minutes. Okay, fine. All right, any questions? I have a few more slides that we'll continue on this, and then I will try to get together an activity where we can work through it, where you can just by almost look at the spectrum and just try to identify the functional group from just 1 or 2 or 3 peaks. Next. Okay. I think, yeah. And the next few slides will be more about watching things change and comparing and contrasting. All right, any questions? I'm going to go ahead and stop recording.